Well, hello and welcome to another episode of Quantitative Bytes. It's great to see you all. I hope you're doing well. So today I wanted to finish off our two-part mini-series talking about colour. If you remember in the previous episode, we talked quite a lot about converting between the RGB and HSV colour spaces, and in particular, we talked about how we would convert a given HSV colour into RGB, and that allowed us to write code to produce this spectrum image that you can see here. And what I want to talk about today, I did promise this would be a two-part series, so for today, the second part, I want to talk about how we do the conversion the other way, how we would, given a particular colour specified by RGB, how do we calculate what the equivalent colour would be in the HSV colour space. So that's what we're going to be talking about today. As I always say, if you like this video, please remember to smash that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future content. I do try to make videos roughly once a week. Now, for the last couple of months, I haven't really been able to achieve that. Everything's been a little bit crazy recently. I don't think I'm alone in that, but hopefully I'll get back to it eventually, and if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, without much further ado, I suggest we jump straight in and let's talk about how we convert from RGB to HSV. If you remember from last time, this is the situation that we had. I'll just recap very briefly. So we have our spectrum across here, and of course this is the hue axis horizontally running from 0 degrees here to 359 degrees here. In this picture we do also have a saturation that varies from 1 at the top to 0 at the bottom, but we are assuming for the sake of this example that we have a saturation of 1 and also a value of 1. So both S and V of HSV are both equal to 1. And what we're interested in today is how we calculate the hue given a particular value of RG and B. So as a second part to this series, in the previous part we looked at how we would calculate RGB from a given HSV value. So in this part we want to discuss how we go about doing that the other way. How would we compute the HSV values if we are given an RGB value? Obviously, it makes sense that we want to be able to do the conversion both ways. So this is the situation that we had before in the previous video. So for all of the values of the hue across here, we have this fairly regular pattern of RG and B values here, which I've marked out in red, green and blue, which hopefully will be visible. And we see that we start off with a red value of 1, 100% red, which then linearly decreases to 0, stays at 0 for 2 of these segments, linearly increases back to 1, and then stays at 1 for one segment. Each of these segments, of course, represents 60 degrees and divides the whole width spectrum, 360 degrees of the spectrum or the hue axis, into 6 equal size elements. And we see then we have the value of green for the first segment goes linearly from 0 to 1, stays at 1 for 2 segments, linearly decreases to 0 for one segment, and then stays at 0 for 2 segments. And similarly for the blue, you can see what's going on there. And in the previous video, we spent quite some time discussing how we use this information to calculate an RGB value for a given hue, and then we went on to discuss the impact of saturation and value. So I want to do something very similar today, except of course we're discussing the conversion in the other direction. So what we want to do is, given a particular RGB value, we want to calculate where we will be along this hue axis. For the moment, we're going to ignore the S and the V components, the saturation and the value, and let's just focus on hue. So given a particular RGB, how do we calculate where we are along this hue axis? Well, actually, it's not perhaps as difficult as it might seem. The first thing that we need to realize is that in any one of these 6 segments, only one of the colors is at a maximum. Okay, so in this first segment here, we see the red is maximum, in the second, green is maximum, in the third, green is maximum, in the fourth, blue is maximum, in the fifth, blue is maximum, and in the sixth, red is maximum again. So what we can do is we can quite easily tell which one of the RG and B values is our maximum. That's very trivial to do in code. And then we can assign an index value to each of these segments based on that. So what I'm going to do is I'm going to write here index, like so. Apologies, it's awkward writing sideways. So we're going to assign this as an index of 1. Okay, and then where the green is maximum, we're going to have an index of 2. Like so. Where the blue is maximum, we'll have an index of 3. And of course red is maximum here, so that is also index value 1. Now, what we need to do is we can see it's very easy actually to calculate which index value we have. We simply test whether red, green or blue is the maximum, and that tells us which index value we need. We'll see that in more detail in code a little bit later on when we go to look at the code. The question comes though then, so we know which one of these 60-degree segments we're in. How do we calculate then precisely where within that segment we are? So if we consider the situation, suppose index is 1, suppose the red is our maximum value, how do we calculate where within this segment we are? So we could be either somewhere in here or somewhere in here. And we can see that what varies here is the green values and the blue values. So if we simply take green minus blue, I'm going to write that over here. Okay, so if we were to take green minus blue, like that. Yep. So we take green minus blue. What that's going to give us is our range here. So we can see that if we're here, so we have blue is 0, green is 0. That's going to be 0 minus 0, which is going to give 0. And if we're here, we have green is 1, but blue is 0, so that's going to give 1 minus 0, which is of course 1, which is what we'd expect. If we're over here, we have blue of 1 and green of 0, so we're going to get 0 minus 1, which is of course minus 1. Now, we're going to come to that condition in a moment. A few things that we have to do. First of all, we have to take into account our linear gradient. Okay, so we take our green minus blue value, and we're going to divide that by the range, which of course is given by max minus min, like so. That's an I. Okay, so that's simply going to divide by our range here. So for the moment, that's the range here in this example is 1, so that's going to be everything divided by 1. That's easy. And then we will need to convert this to an angle. So what we need is 60 multiplied by that. Okay, so now let's just consider some examples when index is equal to 1. Okay, let's just have a look what happens. If we consider the value of green as being 1, the value of blue is 0. Okay, so that's corresponding to here, right? So the value of blue is 0. We're dividing that by 1. That is, of course, 1 minus 0, which is 1, divided by 1, which is also 1, multiplied by 60 gives 60 degrees, okay, which is, of course, exactly what we want. In the other example, when blue is 1, though, what we have is 0 minus 1 there, but we still multiplied by 60 here, we're still dividing by 1 there, and we now see that we have minus 60 degrees, which doesn't necessarily make any sense. And what we're calculating here, these of course are the values of h. Right? Now it's very easy to deal with the possible negative value though. All we need to do is put in a little bit of code like this. We can simply say something like if h is less than 0, then h plus equals 360 degrees. Like that. Okay, so obviously in the situation where we get a value of h that's negative, we can deal with that very easily. We simply detect if h is less than 0, then we add 360 to it, and we can see that if the value we originally have for h is minus 60, we add 360 to minus 60, we get 300 degrees, which obviously corresponds to here, which is of course exactly the right colour. I want to consider one more example. If index is equal to 2, index is equal to 2, let's consider that situation. So now what we're interested in, we see we're here or here, and we know that green is maximum, and what varies now is the value of red and the value of blue. So we know that we're going to be interested in blue minus red. Okay. Just like before, we had green minus blue because those were the ones that vary. Now we have blue minus red because those are the ones that are varying. And as before, we divide that by the range, just given by max minus min, like so. Okay. We're going to multiply that by 60, but now we have an extra component there, because an extra value that we need to add in, because we're no longer interested in a range between 60 and minus 60 that we had before. We now want to go between 60 and 180. So we need to add 2 to this. So we have 2 plus there, and then we multiply all of that by 60. Apologies, making a mess now. So we take all of that and we multiply all of that by 60. Let's just consider that as an example. Let's consider the case that we're here. So we have a value of red, which is 1, and a value of blue that is 0. So that gives us 0 minus 1, okay, here. Now, of course, we're dividing that by 1, because our range is 1. And then we have 2 here, 2 plus that. So 0 minus 1 is obviously minus 1. 2 plus minus 1 is 1. 1 divided by 1 is 1. Multiplied by 60 gives 60. Okay, 60 degrees. Exactly what we want. That puts us here. And let's consider the other example at the other extreme, where we have blue is 1 and red is 0. So now we will have 1 minus 0, like that, divided by 1 as before. Okay. And we're going to have 2 plus, so 2 plus 1 minus 0 is of course 3. 3 divided by 1 is 3, multiplied by 60, 3 multiplied by 60 is 180 degrees, which of course puts us here, exactly in the center. So I think that will make a lot more sense when we come to actually look at the code a bit later on, but this is the basic strategy. This is how, given a particular value of R, G and B, we can calculate the value of H for our hue. And now we need to move on to actually calculate the values for the saturation and the value, the S and the V components of HSV. Okay, so once we've calculated the hue, we need to calculate the values for the saturation and the value, the S and the V components of our HSV color space. So in the previous video, if you have a look back at that, if you haven't seen it already, we worked out how to calculate the maximum and minimum values that we need from the value in the saturation. And in particular, we worked out that the range here, so the range between the minimum and maximum values, is simply equal to the value times the saturation. So the S times S multiplied by V. And also we worked out that the maximum value is simply given by the value, or the V component. And if we bear that in mind, it actually becomes very easy to do the calculation the other way. So, okay, so what we had before was we calculated the maximum value as simply being equal to the value. So of course, that means we can go the other way around. So V, or the value of what we're doing, is simply going to be equal to the maximum value. Let's call this max value. Okay, that's whatever value we have here, so that's really easy. And then how do we calculate the saturation? Well, from the previous video, we know that the range, which is max minus min, so range is equal to value times saturation, or V times S, okay, value times saturation. So if we want to calculate S, that's very simply then going to be the range divided by V, but we know V is equal to max value. So what we have now, range we can write out as max minus min, like that, divided by max. Okay, so we can calculate the saturation as simply being the difference between the maximum and minimum values of our RGB color divided by the maximum, and we can calculate the V, the value, as simply being the maximum value. And that's it. That gives us all of the components that we need for HSV. Now, I think that will become, if anything about that isn't clear, I think it will become clear when we go to look at the code in just a moment. So I suggest we go and do that now. Okay, so here we are at the computer, and we're looking here at the code for the QB color class that we talked about in the previous video. So we're only looking at qbcolor.cpp. That's the only file of that class we need to make changes to today, because the header file that we developed in the last video, that remains exactly fine. We don't need to look at that again. If you need to have a look at the code from the last video, then I'll put a link in the description below so you can go and see that quite easily. So all we need to do now is, the way this code worked before, just to very quickly recap, if the user specifies a color as RGB, then we call our private compute HSV function, which will then do the conversion from RGB to HSV. And if the user specifies a color using set HSV, we then call our private compute RGB function that does the conversion from HSV to RGB. So this conversion from HSV to RGB, or in other words, the code for compute RGB, that's what we did in the previous video. So today we're going to look at what we need to do for compute HSV, and this of course is the function that converts from a given RGB value to the equivalent value in the hue, saturation and value color space. So we don't need to talk about any of the other code that we have here because we covered all of that in the previous video. And just down here, just to show, this is what we did before. This is the compute RGB code that we did. And the code that we're going to do today is simply this code here for compute HSV. And this is actually relatively simple, as you've just seen in the examples that I gave on the whiteboard. This isn't really all that difficult. The first thing that we have to do is determine the maximum and minimum values and which colours out of red, green or blue that they correspond to. So as you saw on the example on the whiteboard, we decided we assigned indices of values 1, 2 or 3 depending on whether the red, the green, the blue was maximum respectively. And in reality we do have an index of 0 corresponding to the case where all of red, green and blue are equal. Okay, we didn't discuss that in the whiteboard example, but I think the need for that is probably fairly obvious. So the first thing we do is define two double variables, or two variables of double precision floating point, is a min value and max value. So obviously to store the minimum and maximum values respectively. And then we have a single byte that we're going to use here, an unsigned char, to store the actual index. And then we very simply work our way through this if, else block here to calculate which is the maximum. So we test if red is equal to green and if red is equal to blue. That's the condition where everything, red, green and blue are all the same, in which case we know that max index is 0. The max value we can set to any one, and the min, so we just set max and min both to red. If we don't meet that condition, of course, then we need to test that if red is the biggest. So we check if red is greater than or equal to green and red is greater than or equal to blue, then we know that index must equal 1. And we know the maximum value is equal to red and the minimum value is either going to be green or blue. And to do that, we do a simple test. We do a simple test. If green is less than blue, then we go green, else we go with blue. Okay, so min value will be either equal to green or blue, depending which is the lowest. Okay, and we do exactly the same for the condition where green is greater than or equal to red and green is greater than or equal to blue. And if none of those were met, then we know we must be in the condition for index 3, and our maximum value must now be blue. And of course our minimum value is now from red and green, and as before. Okay, so that's all fairly self-evident. So once we've done that, we now have our index and we have our maximum and minimum values, and now we can use those to compute the value of h. Now this is exactly as we just talked about for the whiteboard example. So we use a simple switch statement to switch over the value of max index. And remember, max index is either 0, 1, 2 or 3. In the case that max index is 0, we know that h has to be 0 and we stop. We break out of the switch block. There's nothing else that we need to do. If index is equal to 1, we know that h is equal to 60 multiplied by the green value minus the blue value divided by max value minus min value. Of course, max minus min is the range. So this is exactly the equations that we saw on the whiteboard just now, and then we break out of the switch block. If index is 2, then exactly as we saw on the whiteboard before, we now have 60 multiplied by 2 plus blue minus red divided by the range. And the only example that we didn't discuss on the whiteboard is the case when h index is max index is equal to 3, in which case we have 60 multiplied by 4 plus red minus green. So the reason we use 4 plus is the same reason we use 2 plus here. I think if you look back at the diagram we drew on the whiteboard, the reason for that will become quite obvious. And that's it, really. That then gives us our value of h, except for one thing. We have to apply the correction if h is less than 0. So in this condition here, it is of course possible for h to vary between minus 60 and plus 60. So we have the simple test. If h is less than 0, then we do h plus equals 360 degrees, which is exactly the same as the example that I showed on the whiteboard just now. And then we compute the saturation. Well, that's very simple, as we just saw. We test initially if max index is equal to 0. So in the case that max index is equal to 0, we know the saturation has to be 0. So we simply test if. So if max index is equal to 0, then S is set equal to 0. Else, it's simply set to max value minus min value divided by max value. That's the equation we just saw on the whiteboard now. And the value V simply equal to the max value. And then we simply store that result into our classes. H, S, and V are stored into m underscore hue, m underscore saturation, and m underscore value, respectively. And that's it. That's actually all of the code that we need to convert a color, given any RGB color, into the HSV color space. So the only thing left then to talk about is exactly how we test this. Now obviously going the other way, converting from HSV to RGB, we could test that quite easily by generating the nice spectrum image. Because we get the right spectrum, we know that everything works correctly. Going the other way is not quite so aesthetically pleasing in terms of testing, and the best way I found to do it is to just produce a very simple table of values for standard colors. So in capp.cpp, again we talked about this in the previous video, so I'm not going to go over all of the code here again. You can go back and look at the previous video if you want to recap about that. But all we do now in the initialize method, and I've deleted everything here now to do with tick and everything, so this code doesn't really do anything except produce a blank window that you can then close. But in the initialize block here, so capp : initialize, I've gone ahead and created a vector of type QBColor. That's of course the QBColor class that we've created, simply called test colors, and then I go and assign to that a series of standard colors. So we assign to it black, which in terms of RGB. Okay, that's important. So we're specifying our colors in terms of RGB, and what we're going to do is see if we get the correct corresponding HSV values for each of those. So we push back first of all black, which is 000, white, which is 111, and then the other colors here for red, green, blue, yellow, cyan, magenta, dark red, olive, dark green, purple, teal, dark blue, mid-grey, and dark grey. Now I think that represents a fairly comprehensive test of everything, and there are plenty of standard color charts available on the web. You can just Google for one to have a look for what the corresponding HSV value should be for any of these. And I have done that, and I've tested for this range of values and compared the values that I get for HSV for these RGB values, and I believe that they are correct. Of course, you know, this is code is provided as is, so test it. If you want to use this code for anything, I do suggest you test it thoroughly yourself. Don't simply assume that I've necessarily got everything absolutely right, because I can make mistakes just like anyone else. But I have conducted this test, and to the best of my knowledge, this indicates that the code in QBColor does indeed work correctly. But as I say, best to test it yourself to confirm that. And once we've done that, all we do is we produce a nice table of the output. So I'm using the std : set w to set field width for our output, which simply is a nice way of producing nicely formatted text output. So we produce a table with columns for red, green, and blue, and columns for H, S, and V. And then we simply loop over every color in test colors. So for QBColor current color in test colors, and then we simply populate the table accordingly. So we get the red, green, and blue values out of that, which are simply going to be the values you specified. And then we use get hue, get saturation, and get value using the F of the floating point versions to get the corresponding floating point values for that, which should give us a nice table that will allow us to see whether our conversion has indeed worked correctly. So if I go to my terminal window, I've already compiled this code and everything else, so we don't need to worry about that. So if I simply run main, which is the name of the main executable, and close that window, what we see that we get here is very simple. We get a table, so we have our RGB values and the corresponding hue, saturation, and value. So we see that, look here, the first row, if RGB is 000, which is of course black, we have hue, saturation, and value that are all black. For RGB of 111, which is of course white, we have hue 0, saturation of 0, value of 1, which is correct. For red, 100 in RGB, we have hue of 0, saturation of 1, and value of 1. And so on. So green comes at 120.11, blue 240.11, yellow, which is 110 in RGB, is 60.11, and so on. I'm not going to go over all of those. And as I say, you can look these up in any standard table of colors or converting tool on the web. If you just Google for it, there are many examples, and you can test this for yourself that it does indeed work correctly. And actually that's it. That's all of the code that I really wanted to talk about today. And I think what we've presented here, what we've created here is a very simple class for handling color. It allows the user to specify colors in terms of either RGB or HSV as they see fit in either floating point or unsigned char types. and it allows the user then to retrieve the color in whatever color space, RGB or HSV, that they wish, and it takes care of all of the conversions and everything internally, which I think actually makes quite a useful little class there for handling color. So there we go, that's everything I wanted to talk about today, and that concludes this two-part mini-series on converting between colour spaces. Obviously there are lots of other colour spaces that we could consider, and we could think about. RGB and HSV are definitely not the only two. However, I personally have found these to be the two most useful ones, and when I come later on, later this year or possibly early next year, I'm going to start looking at some stuff where we're going to talk about shading of different colours and calculating reflections and shadows and things and that sort of thing. And in that situation, being able to represent colours in terms of the hue, saturation and value, or HSV, is actually really very useful, but we'll see more about that later. Anyway, for now, I really hope these two videos together create something that's useful to at least some of you out there. And, you know, I really hope you've enjoyed this video. It's been a great deal of pleasure making it, so I hope you've enjoyed it. And as I always say, if you have enjoyed this video, please remember to hit that like button. And if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future content. Thank you very much for watching. I really look forward to seeing you in the next video. Bye.